Imagine stepping outside one ordinary morning and feeling your skin burn within minutes. Not from heat, not from fire, but from sunlight that has suddenly turned lethal. High above your head, something invisible but essential has failed. The ozone layer, Earth's natural sunscreen, now has a hole the size of Africa ripped through it, an opening so vast that it stretches across continents. And through it, the sun is no longer filtered, it is unleashed. Within hours, ultraviolet radiation floods the surface below the hole. Crops begin to wither as their DNA is damaged beyond repair. Oceans shimmer strangely as microscopic plankton, the base of the entire marine food chain, start dying en masse. Hospitals overflow with people suffering severe sunburns, eye damage, and radiation sickness, even on cloudy days. This isn't a slow disaster, it's instant. Satellites detect massive spikes in UVB and UVC radiation, levels usually blocked completely by the ozone layer. Skin cancer rates don't rise over decades, they explode in weeks. Animals that evolved under a protective sky suddenly have nowhere to hide. Birds fall silent, insects vanish. Ecosystems begin collapsing from the bottom up. And the most terrifying part? You wouldn't see the hole. No smoke, no fire, no warning sirens. Just sunlight doing what it has always done, but now without restraint. This is not science fiction. Smaller ozone holes already exist. We know what happens when the shield weakens, but scale that damage up to something the size of Africa. The question is no longer what would change. It's how long could life survive? Please like this video, subscribe to the channel, and comment your question below. Let's clearly define the nightmare we're exploring. The ozone layer is a thin but vital region of gas located about 15 to 35 kilometers above Earth's surface. Its job is simple and absolutely critical. It absorbs most of the sun's harmful ultraviolet radiation, especially UVB and UVC rays that can damage DNA, kill cells, and disrupt entire ecosystems. Without it, life on land as we know it would never have evolved. Now imagine a single, continuous ozone hole the size of Africa, not a seasonal thinning like the one over Antarctica, but a permanent, massive rupture. This hole spans millions of square kilometers, exposing multiple countries, oceans, and climate zones to direct, unfiltered solar radiation every single day. Why is this scenario scientifically interesting? Because it pushes a real, well-understood phenomenon to an extreme scale. We already know what ozone depletion does in small doses: increased skin cancer, crop damage, harm to marine life, and disruptions to climate patterns. This scenario asks a bigger question. What happens when the shield fails catastrophically? In this video, we'll explore how such a hole could affect human health, global ecosystems, weather systems, and even Earth's long-term habitability. We'll break it down step by step, starting with the most immediate and devastating consequences, then following the chain reaction as it spreads across the planet. This isn't about instant extinction, but it is about how fragile Earth's balance really is, and how quickly that balance can unravel when one protective layer disappears. The very first consequence of an ozone hole the size of Africa wouldn't be climate change or rising temperatures, it would be biological shock. With the ozone layer gone over such a massive region, ultraviolet radiation, especially UVB, would slam directly into the surface. These rays penetrate living tissue and damage DNA at the molecular level. Cells mutate faster than they can repair themselves. Life doesn't slowly adapt, it breaks. For humans, the effects would be immediate. Severe sunburns would occur in minutes, even during early morning or late afternoon. Protective clothing becomes essential just to survive outdoors. Eye damage skyrockets as UV radiation causes corneal burns and rapidly increases cases of cataracts and permanent blindness. Skin cancer rates don't rise gradually over decades, they surge within months. Animals suffer even more. Many species rely on fur, feathers, or thin skin that offers little UV protection. Amphibians, already sensitive to radiation, experience mass die-offs as their eggs fail to develop. Livestock exposed to open sunlight develop lesions, infections, and reproductive failure, threatening food supplies almost instantly. Det bör katastrofen efter Zanzibar för skapligt in the tropical naturvärld. But det kan specific equal the summer spike in civic. Phytoplankton, microscopic organisms floating near the top of the sea, are responsible for producing over half of Earth's oxygen and form the base of the marine food web. UV radiation penetrates clear water, killing plankton in enormous numbers. As plankton populations crash, fish larvae starve. Then small fish disappear, then larger predators follow. Entire ocean ecosystems begin collapsing from the bottom up. Plants on land aren't spared either. UV radiation interferes with photosynthesis, stunting growth and reducing crop yields. Wheat, rice, corn staples of global civilization begin to fail under open skies. In real life, scientists observed similar but smaller effects during periods of Antarctic ozone thinning. This scenario simply removes the brakes. The result? A biological emergency unfolding faster than governments or ecosystems can respond. Once the biological damage begins, the planet doesn't stabilize, it spirals. As phytoplankton populations crash beneath the ozone hole, the ocean loses one of its most important climate regulators. These microscopic organisms don't just support marine life, they also absorb massive amounts of carbon dioxide. With fewer plankton pulling CO2 from the atmosphere, greenhouse gases begin to accumulate faster, intensifying global warming. At the same time, large areas of land become functionally uninhabitable during daylight hours. Vegetation thins or dies off, exposing soil directly to sunlight. Without plant roots to anchor it, the ground dries, cracks, and erodes. Dust storms increase, carrying fine particles high into the atmosphere. Here's where the chain reaction accelerates. Those airborne particles interact with sunlight and clouds, altering atmospheric circulation. Weather patterns shift unpredictably. Some regions experience relentless drought, while others are hit by extreme rainfall and flooding. Monsoon systems weaken or collapse entirely as temperature gradients in the atmosphere break down. Meanwhile, the ozone hole itself begins affecting global wind systems. The stratosphere above the exposed region cools abnormally because ozone normally absorbs heat. This temperature imbalance distorts jet streams, pushing storms off their usual paths. Heat waves strike places unprepared for them, while cold snaps hit agricultural regions at the worst possible times. Wildfires become more frequent and more intense. UV damaged plants ignite more easily, and dry conditions turn forests into fuel. Smoke from these fires further blocks sunlight in some regions while trapping heat in others, creating a feedback loop of chaos. Even regions far from the ozone hole feel the impact. The atmosphere is a connected system. What breaks in one place sends ripples everywhere. Earth doesn't just lose a protective layer, it loses predictability. As years pass under an ozone hole the size of Africa, the crisis shifts from immediate survival to planetary transformation. With ecosystems collapsing and agriculture failing across exposed regions, mass human migration becomes unavoidable. Entire populations are forced to abandon sun blasted zones, seeking refuge in higher latitudes or underground environments. Cities adapt by building UV shielded domes, covered walkways, and daylight curfews. Life on the surface becomes limited, cautious, and artificial. Evolution itself begins to feel the pressure. Species that survive develop thicker skin, protective pigments, or nocturnal lifestyles. Some plants evolve waxy coatings or altered leaf structures to reflect radiation. But evolution takes generations, and many species simply don't have that time. Extinction rates skyrocket, pushing Earth toward a biodiversity to rivaling the greatest mass extinctions in geological history. The climate continues to destabilize. With reduced vegetation and plankton, carbon cycles weaken, oxygen production drops slightly, but dangerously, while carbon dioxide continues to rise. The atmosphere slowly becomes less friendly to complex life. Not deadly overnight, but subtly hostile over centuries. One unexpected consequence emerges: technological dependence becomes absolute. Survival now relies on filters, protective materials, artificial food systems, and controlled environments. Civilization doesn't end, but it transforms into something far more fragile. A single system failure could mean catastrophe. Could Earth recover? Possibly, but only over very long timescales. Natural ozone regeneration would take decades or centuries, assuming the cause of the damage stopped completely. Until then, the planet remains wounded, and life limps forward under a harsh, unforgiving sky. This scenario doesn't erase life from Earth. It rewrites the rules for who gets to survive. Let's take a step back and look at what just happened. A single rupture in the ozone layer expanded to the size of Africa set off a chain reaction that reshaped the entire planet. It began invisibly, high above the surface, but its consequences reached every corner of Earth. Unfiltered ultraviolet radiation turned sunlight from a life giver into a biological weapon. Humans, animals, plants, and oceans were all struck at the cellular level. The first systems to fail were the smallest ones: plankton, insects, crops, and fragile species. But from there, the collapse spread upward. Food chains unraveled. Weather patterns lost their balance. Climate systems became erratic and hostile. What started as a chemical failure in the atmosphere evolved into a planetary emergency. Yet Earth did not become lifeless. Instead, it became less forgiving. Survival shifted from open skies to shelters, from natural balance to engineered protection. Life adapted where it could, vanished where it couldn't, and relied increasingly on technology to fill the gaps nature once handled effortlessly. The planet remained alive, but wounded, unstable, and permanently changed. This scenario reminds us of a powerful truth. Earth's most important defenses are often invisible: thin layers of gas, tiny organisms, delicate balances we rarely notice until they're gone. The ozone layer is only a few parts per million of our atmosphere, but without it, the world above us becomes a threat instead of a shield. And the most unsettling thought of all, we already know how to damage it. The real question is whether we choose to protect it in time.